This section is 9.5 and it involves alternating series. I think overall some of this material is a little easier to understand than other portions of this section. I highly recommend that you spend a little bit of time in this section. So watch as many as the CalcView videos as you can, read through the text if you can, and practice as many problems as you can. So basically, one type of series we've seen before is an alternating series. And this example here is an alternating series because the signs alternate. So if you look at this example, we have alternating signs, and that is determined by this here. So we've seen something like this. Now this is an alternating geometric series with r is equal to 1/2. This is less than 1, so this series converges. So alternating series occur where either the odd terms are negative or the even terms are negative. So there's both types. So here is the theorem. So just another one to add to the list. This is the alternating series test. Basically, this is saying that either alternating series, whether it's the even terms or the odd terms, that alternating series will converge when two conditions are met. These two conditions must be met in an alternating series in order for it to converge. The limit of the series must be equal to 0, and for a to the n, a sub n plus 1 must be less than or equal to a sub n. Now, if the first condition does not pass, then you can use the nth term test for divergence to conclude that the series diverges. Just because, to remind you, if the limit as n approaches infinity of that series does not equal 0, then by the nth term test, the series diverges. Okay. All right. So what we're going to do is we're going to do a handful of examples here. And whenever we are given the function, the first thing we're going to do is we're going to verify that the limit equals 0. If the limit equals 0, then we'll go on and verify this second step. If the limit does not equal 0, then we will draw this conclusion down here. Okay. So here's our first example. Now this here, we know it is an alternating series because of this piece here. So what we're going to do, that piece is, you know, it's something we're just going to kind of set aside for now. And really, we're going to focus on our sequence, or I'm sorry, our series being this. Okay. So what we need is the following. We need the limit as n approaches infinity of a sub n to equal 0. And we also need, so this is the first thing, the second thing we need is for the second term to be less than the term before it. Okay, so for us, for part 1, I want to evaluate this limit. So the limit as n approaches infinity of 1 over e to the n. Okay, well, if I plug infinity here, e to the infinity, this is getting bigger and bigger and bigger and bigger. So this is equal to 0. Excellent. Our first requirement is met. Okay, the next one. All right, so what we need to do is, if we know this is a sub n, I can find a sub n plus 1. A sub n plus 1 is simply this function, but instead of n, we plug in n plus 1. So this is equal to 1 over e to the n plus 1. Okay, well, we need to verify that this is less than or equal to 1 over e to the n, which is our a sub n. Okay, so this piece here is this, and these are equal. So we just want to verify that this is a true statement. Well, if I rewrite this using properties of exponents, I can write this as e to the n times e to the first, or just e. Well, this is getting bigger faster than this, which means this is, in fact, less than or equal to this. So our second condition is met. So we can conclude that both are satisfied. So both conditions are satisfied. So the series converges by the alternating series test. Now, one thing I would like to note is that this is a convergent geometric series. Okay, so FYI, but on a test or quiz, this is something that you will want to illustrate. All right, let's take a look at another example. It says determine the convergence or divergence of this series. Again, this piece here tells us what's alternating. This tells us it is an alternating series. So really, we want to focus on everything else. So I'm going to say that a sub n is equal to n over 3n plus 2. Okay, so if that's the case, then we want to see if our two conditions are met. So remember, we need the first condition to be met, which is the limit as n approaches infinity of a sub n equals 0. So for us, the limit as n approaches infinity of n over 3n plus 2, well, here we have the same degree on the top and the bottom, so my limit is going to be the ratio of coefficients, which is 1/3. Well, this does not equal 0, so our first condition is not met. So I told you that if that condition's not met, then we go to the nth term test for divergence. So we can conclude, since the limit as n approaches infinity, please excuse my puppy, a sub n does not equal 0, then by the nth term test, the series diverges. Okay, so I've shown you an example of each. I think it would be in your best interest to try to watch some more videos so you can see some more examples of how these are done. Okay, let's take a look at something else. All right, so here's another theorem. It's the alternating series remainder theorem. And this is something a little bit different, but basically, if we have a convergent alternating series, so it has to be convergent, so that means parts 1 and 2 must be satisfied of the alternating series test. Well, sometimes a partial sum can be useful in making an approximation for that sum. And sometimes we're interested in finding the error by a partial that would be created by a partial sum. So this alternating series remainder theorem, again, it has to be convergent, and you can read through this, but basically what this is saying is if S is the actual sum, and this is our approximated sum, so this is our partial sum, the difference between these is the remainder, and that remainder is less than the n+1 term. Now, I don't know about you, but when I first saw this, I'm like, okay, mind blown. What just happened? So let's just dive into some examples and see what it is I'm talking about here. Okay, so here is the first example, and it says approximate the sum of the series by using the first 6 terms. So what we're going to do is we are going to first check for convergence, so we can see that this is an alternating series. I kind of forgot the whole thing. There we go. So this tells me it's an alternating series. I'm going to verify that it's a convergent alternating series. Once I do that, then I'm going to find the partial sum of the first 6 terms, and then I'm going to apply the alternating series remainder theorem to see how close that approximation is. Okay, so there's kind of a lot going on here, but let's get started. So the first thing, we're going to check for convergence. Okay, so when we do that, the first thing we need to verify is that the limit of whatever's left, so that would be 4 over the natural log of n+1, we want to make sure that this is equal to 0. Well, if infinity goes in here, the denominator is increasing extremely fast, which means this is in fact approaching 0. Boom, the first one is achieved. The second one, we want to make sure the n+1 term is less than the nth term. So a sub n+1, all I'm going to do is plug in n+1 right here. So this is really 4 over the natural log of n+2. This needs to be less than the nth term, which is this. And again, it is. Okay, so woohoo. Our function is convergent. So now, step 2, what we're going to do is we are going to find the partial sum. Okay, now we are starting with n is equal to 1. So what I'm going to do, if I want to find the sum of the first 6 terms, I'm going to plug 1 in and then add that to what I get when I plug 2, 3, 4, so on and so forth. Okay, so when I plug 1 in, I end up with the following. When I plug 2 in, I end up with the following. When I plug 3 in, and we just keep trucking along to the 6th term. This is so fun. Okay, so this is my 6th term here. Now notice that the exponent and the argument of the log function, these are 7. That's because we started with n is 1. Okay, so I'm just going to save some time here. Well, all right, I'll keep going. That's fine. All right, so this is 4 over natural log of 2. Then this is minus 4 over natural log of 3. Plus 4 over natural log of 4, minus 4 over natural log of 5, plus 4 over natural log of 6. And I think you can see this pattern here. Okay. Now, if I were to plug all of this into my calculator, I would get approximately 2.7067. Okay, so remember, this is the sum of the first 6 terms. Okay, so this is an approximation of this sum. Now we want to know how accurate this approximation is. And that's why the alternating series remainder theorem is helpful. So our third step is to apply the alternating series remainder theorem. Okay. And remember that theorem states the actual sum minus the approximated sum is equal to the remainder, and that has to be less than or equal to the nth plus 1 term. Okay, now our n here is 6 since we are dealing with the first 6 terms. So what we have, so this is going to be the absolute value of our 6 must be less than or equal to, if this is 6, this has to be less than or equal to our 7th term. Now our 7th term is found by plugging in 7 up here. Okay, this is what we get when we plug in 6. So when we plug in 7, we'll get a positive 4 natural log of 8. And this is approximately 1.9236. Okay, so what we've just found is this piece here. Okay, so now we're going to take a look at this piece. All right, so the absolute value of s minus s sub 6, now this is the actual sum minus the approximated sum. This has to be less than or equal to our 7th term, and we just found our 7th term to be this. Okay, well, let's just apply some, well, we'll plug in this, so this will go right here. But then let's apply our rule of absolute values. Okay, so I'm hoping you remember this. Remember, the absolute value of something is going to be sandwiched in between these two values. So the negative value of this has to be less than or equal to this. And I'm going to plug this decimal instead. Okay, so I have eliminated the absolute value just using algebra. So now I'm going to add this 2.7067 to both sides. Okay, so what I can conclude now, when I add this, I get 0.7831 is less than or equal to s is less than or equal to 4.6303. Okay, so what I can say is the following. My actual sum, the actual sum of this series is in between these values. Well, our approximated value certainly is in between these values, so that is great. Good news here. Now this problem is similar, but something a little bit different than something else we could see utilizing that alternating series remainder theorem. Just something a little bit different. Now it says to use that theorem to determine the number of terms required to make an approximation of the sum with an error no less than 0.001. Okay, so let's take a look at this. By this theorem, so by theorem 9.15, we know that our remainder must be less than or equal to the nth plus 1 term. Okay, well, this piece here, remember, discusses the alternating series part. Okay, so our nth term, so a sub n is 1 over n squared. So if I'm talking about the nth plus 1 term, this is going to be 1 over n plus 1 quantity squared instead. Okay, so we want this to have an error less than this decimal here. So I'll make the following statement. For an error less than, n must satisfy the following. Okay, we want this to be less than, just less than this. Okay, so this is by the theorem. Okay, we want that to be true. All right, well, what I can do is I can multiply both sides by this denominator. And when I do, these cancel, so I'm left with 1 is less than this. Okay, well then I divide by this, and when I divide both sides by this decimal, 1 over that is really 1,000. 1 divided by 1,000th is 1,000. Okay, then I take the square root of both sides, and when I take the square root of both sides, I end up with this approximation over here, less than n plus 1. Then if I subtract 1 from both sides, I end up with this. So this is saying that n has to be greater than this. But what does this mean? So what this means is, that sounds weird. Here's what it means. Since I wanted to find the number of terms required to have an approximation with an error less than this, I need at least 31 terms. So I want to use 31 terms in order for my approximate sum to have an error less than this. Okay. All right, let's move on to something else. Now we're going to talk about absolute and conditional convergence. So here, basically what this is saying that sometimes a series can have both positive and negative terms, but it's not an alternating series. And this is an example of that. So this will have positive and negative terms, but it doesn't alternate. So what we can do is we can take the absolute value of this, as shown here, and investigate this. And if we look into this, this will tell us some things. So when I compare the functions, so this was one of them, and this is the absolute value. then we know that that this is less than or equal to this by the direct comparison test, and so we can find some convergence. Now, I know I'm kind of waving my hands through this a little bit because I think showing you examples will make this make a little more sense than what it may right now. So another theorem, this is the absolute convergence theorem. It says that if a series, if the sum of the absolute value converges, then the series also converges. So that's why it's important that we're looking at the absolute value of that series. Okay, so there's something called absolute convergence and conditional convergence, and that's what's shown here. So the converse of the theorem that I just stated is not necessarily true. And basically, here's what I'm showing. So if I have this alternating harmonic series, okay, so it's a harmonic series, but it's alternating signs. Well, this series converges. However, the harmonic series all by itself diverges. So if the alternating harmonic series converges, but the harmonic series diverges, then this is called conditional. And this is rather important. So definitions of absolute and conditional convergence is the following. If the series, the sum of the series is absolutely convergent, this will happen when the absolute value converges. It's called conditionally convergent when the series converges, but the absolute value of it diverges. Okay, now, holy cow, I know that's a lot going on, and you are probably thinking, what the heck is she talking about? And quite frankly, I don't blame you for thinking that. But let's just take some baby steps and look at another example. Okay, so this says determine whether the series converges absolutely or conditionally, or if it diverges. Okay, so the first thing we want to do, step one, we want to determine if the absolute value, the abs value converges. Sorry, my puppy's being special. If so, then it will converge absolutely. Okay, so this is what we are going to investigate. I'm interested in this sum, but the absolute value of it. Okay, all right, now if I look at this part here tells me it's alternating. Okay, fine. And this part here tells me that no matter what, it's always going to be positive. So if I take the absolute value of this, this is equal to this. Okay, well, this is a p-series. This is a p-series with p equal to 2. Since 2 is greater than 1, we can say that this series converges. I'm really sorry, my puppy is just being special. Hang on, let me get her a bone. Okay. She didn't even say thank you. I'm going to have to work on her manners. Okay, so since this p-series converges, if I look back at that definition, it says if the absolute value converges, then this is absolutely convergent. So we can conclude, so therefore, the given sum converges absolutely. Okay, so that wasn't so bad. Let's take a look at another example. Here it says same thing, determine whether the series converges absolutely or conditionally, or if it diverges. Okay, well, step one, we want to find the absolute value of this here. Okay, so let's take a look. Step one. Absolute value of the given. All right, well, again, this is just the alternating part. That's either going to be positive 1 or negative 1. So that doesn't really matter. The absolute value of that is going to be 1. The absolute value of this, since n is 1, this will also be positive. So I can say that this is equal to 1 over n plus 3. Okay. Well, looking at this, I'm going to apply the direct comparison test. Okay, so since I'm going to apply the direct comparison test, I'm going to compare this to 1 over n. Now, 1 over n diverges. Okay, so hopefully you can understand that that diverges. So we can say, therefore, since 1 over n is less than 1 over n plus 3, so I'm comparing these two functions since this is less than this, and this diverges, then this also diverges. Okay, now this tells me that the absolute value of our function diverges. Okay, so this eliminates absolute convergence. Okay, because in order for this to be absolutely convergent, the absolute value must converge. And our absolute value diverges, so this is not absolutely convergent. Okay, so since we've done that, now what we want to do is we want to apply the alternating series test to see if it converges conditionally. Okay, so this is going to be step 2. Apply. That doesn't say apply. Apply the alternating series test to see if it converges conditionally. Okay, and that's just from the definition of absolute and conditional convergence that I showed you on a previous slide. Okay, well, applying this alternating series test, remember two items need to be fulfilled. The first one, the limit of 1 over n plus 3, that has to be equal to 0. And in our case, yeah, that limit does equal 0, woohoo. Okay, now we're going to do the same type of thing that we did in other slides, and we're going to see what this is. Well, if I plug in n plus 1 here, I get 1 over n plus 4. This is less than or equal to 1 over n plus 3. Yeah, that's true. So since this is true, we can conclude that this series converges. Okay. So the absolute value diverges, but this converges. So that means, so therefore, the given function, the given series, converges conditionally. Okay. I'll show you one more example. It says determine again whether the series converges absolutely or conditionally, or if it diverges. Okay, so step 1, we want to analyze the absolute value of this. Right, not so bad. So when I do this, this just tells me what alternates. Okay, so this is equal to n over 5n plus 1. Well, I'm starting with n equals 1, so anything 1 or bigger is what I'm interested in. So this is equal to the following. I can basically omit the absolute values. Okay, well, if I want to find this sum, I can apply the limit test or the nth term test, or lots of them. But if I want to find this limit of this, these degrees are the same, so this limit is equal to 1/5. Well, 1/5 does not equal 0. So I can say that this series, so therefore, this series diverges by the nth term test. Okay, so if we find right away that our series diverges, then we don't have to worry about any of this convergent part because it diverges and we're done. Isn't that lovely? Okay, now this wraps up this section, but I have a note to tell you guys to watch a video, but I have no idea what video I'm referring to. I'm assuming it is the CalcView videos. So as mentioned at the beginning of this, make sure you watch the CalcView videos for this section. Good luck!